Hello again. Today we're going to go over problems from chapter 28. So this is the chapter on the sources of the magnetic field. So we have 6 recitation problems and 4 homework problems. So let's get straight to taking a look. So the first problem is problem number 6. An experiment on the Earth's magnetic field is being carried out 1.00 meters from an electric cable. What is the maximum allowable current in the cable if the experiment is to be accurate to 2.0%? So basically, what magnetic field due to the current in the cable, and we can assume it to be a long straight wire, and we're a distance 1.00 meters away from it. So what current would be sufficient to cause a 2% error in a measurement of the Earth's magnetic field 1.00 meters away? Take 5.00 times 10 to the negative 5 Tesla as the magnitude of the Earth's magnetic field. Then we move on to number 10. A straight stream of protons passes a given point in space at a rate of 2.5 times 10 to the 9 protons per second. What magnetic field do they produce 2.0 meters from the beam? So you're going to have to convert that protons per second to coulombs per second or amperes, and then figure out what magnetic field they produce 2.0 meters from the beam. So you can think of a beam of any type of charged particle as being the equivalent of a current as far as determining the magnetic field is concerned. Then we move on to number 18. A rectangular loop of wire is placed next to a straight wire, as shown in figure 2837. So you basically have a straight wire going across and then a rectangular loop below it. And so you'll need to figure out the directions by looking at the figure. There is a current of 3.5 amps in both wires. Determine the magnitude and direction of the net force on the loop. So the horizontal segments on the rectangular loop, you should be able to figure out. The vertical segments, if you wanted to figure them out individually, that would require integration. But if you look at the problem, you'll realize you don't have to figure that out. Then we move on to number 29. A 20.0 meter long copper wire, 2.00 millimeters in diameter, including insulation, is tightly wrapped in a single layer with adjacent coils touching to form a solenoid of diameter 2.50 centimeters, the outer edge. What is the length of the solenoid and the field at the center when the current in the wire is 16.7 amps or amperes? So the length of the solenoid is basically the length of the cylinder. And you have basically the length of the cylinder is going to be the diameter of the wire multiplied by the number of turns in the coil of wire. And so that will give you the length of the solenoid. So you need to figure out capital N, the total number of coils in the wire, in order to figure out what A is. And then once you know A, figuring out B is pretty straightforward. So that brings us to number 34. A wire in a plane has the shapes shown in figure 2843. So 2 arcs of a circle connected by radial lengths of wire. And you're asked to figure out the magnetic field at point C, which is basically the center of curvature. So you have the 2 arcs of the circle. C is at the center of curvature. So you need to figure out the DL and R and the cross products and then do the integration. I'll say this much, the integration isn't that hard once you get to it, and you should be able to figure out what segments of the wire give you no magnetic field at point C. And that brings us to number 35. A circular conducting ring of radius R is connected to exterior straight wires at 2 ends of a diameter. So basically you have a circle and the current goes in both directions and then reconnects. And so the current splits into unequal portions. So the circular segments do not get the same current. And so while passing through the ring, what is B at the center of the ring? And so you can use the right-hand rule to figure out the direction. And everything else I think you can figure out. And again, as always, if you have any questions or you're not sure that you have the correct answer, please send me an email and let me know. and I'll be able to help you. That brings us to the homework problems. So the first is number 9. A long horizontal wire carries 24.0 amperes of current due north. What is the net magnetic field 20.0 centimeters due west of the wire if the Earth's field there points downward 44 degrees below the horizontal and has a magnitude 5.0 times 10 to the negative 5 Tesla? So you have the current, and the current is pointing due north. So you figure the magnetic field out from that, and don't forget that you have the Earth's magnetic field involved as well. So you want the net magnetic field. So you have the Earth's magnetic field, and then you have the magnetic field due to the long straight wire. So you can, so there's a couple of steps to this problem. Then we go to number 12. 2 straight parallel wires are separated by 6.0 centimeters. There was a 2 amp current flowing in the first wire. The magnetic field strength is found to be 0 between the 2 wires at a distance of 2.0 centimeters from the first wire. What is the magnitude and direction of the current in the second wire? So there's a point in between the wires where the magnetic fields due to the wires cancel each other out. And from that, you should be able to figure out the magnitude and direction of the current in the second wire. Now we move on to number 28, a toroid. And again, that's not the cylindrical coil, that's a donut-shaped coil. So it's wrapped around, and then that goes in a circle as well. Has a 50.0 centimeter inner diameter and a 54.0 centimeter outer diameter. It carries a 25.0 amp current at 687 coils. Determine the range of values for B inside the toroid. So you know what the equation for the magnetic field inside a toroid. You figure it out at the outer edge, you figure it out at the inner edge. And that brings us to number 40. Consider a straight section of wire of length D, which carries a current I. Show that the magnetic field at a point P, a distance R from the wire along the perpendicular bisector. So basically you draw a line halfway through the wire that's perpendicular. And you go a distance R away from the wire along that line. And you figure out the magnetic field. So it's not all that different from integrating for the magnetic field due to an infinite long straight wire. This difference is that the lengths are finite. So you'll have to evaluate that sine function at 2 different points. And then show that this is consistent with an example 2811 for an infinite wire. So if D goes to infinity, how does your end result look? Okay, so those are the 10 problems. Now 6, you should be able to present a video for tomorrow. So I've given you your partners for the week. And again, if you have any questions, and especially if you're uncertain that you have the correct answer, please send me an email and ask for help. Okay, thank you very much.